This morning in North Carolina, wheels are spinning. Determination is winning. A passion is now a thriving business, and it shows no signs of slowing down. How? The power of a conversation, like the one Clint Spiegel had with First Horizon Bank about starting a bike wheel manufacturing facility in Asheville. Now it's not just talk, it's rubber meets road. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint. First Horizon Bank, member FDIC.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on the Space Nuts podcast, where we talk astronomy and space science. It's great to have your company again this week. My name's Andrew Dunkley. I am your host. I don't do anything, but we will be talking with the good Professor Fred Watson shortly. Today on the program, we're going to look at the age of moon rocks, and you can tell the age of moon rocks because of the use-by date that's on the bottom of them all. But on a serious side, the Chang'e 5 mission up there at the moment, and what they've discovered has been quite surprising. So we'll be looking into that, as well as radio signals discovered from distant stars. And audience questions. We've got a new batch of audio questions. Dr. Robert Scott on the Sunshine Coast wants to ask us a couple of questions about the temperature of a black hole and what is space-time made of. It's made of space and time, so I'm told. And Martin from Wollongong wants to know why Jupiter and other gas giants haven't been turned into rocky planets by asteroids after billions of years of impacts, which is a really good question. We'll look into that, as well as many other things. Joining us, as always, on Space Nuts is the good professor himself, Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How's it going?
Oh, good. We're out of lockdown.
Yeah,
we're out of
that's
lockdown.
Right. But we're not totally out, because I can't come and see you in Dubbo and you can't come and see me in Sydney.
No,
However,
Sydney's off limits, so I can't go and see my boys, but I can go and see me mum.
Yeah, I can see your mum, that's right. Yeah.
Yeah. But I became a great uncle this week.
Wow, that's impressive.
Yeah. My nephew and his partner had a baby girl on Freedom Day, as they called it, on Monday.
11th of October.
Yeah, so that was a lovely surprise. So it was a double bonus day for us, so very, very happy.
And it used to be my Auntie Dot's birthday as well. There you go. So
there you are.
There's a connection there. She's no longer with us.
Now, Fred, we have got a little bit to tackle today. Now, we've talked about the Chang'e 5 mission on a few occasions. In fact, I think we probably mentioned the Chinese moon mission last week, having cracked 1,000 days on the lunar surface, which is a great milestone. But now there's some more news on what's happening on the moon with the Chinese mission Chang'e 5, etc.
Yeah, that's right. So I think it might be Chang'e 4 that was the 1,000-day.
Yeah, it might be too.
Yeah, because that's the one on the far side of the moon.
That's exactly right.
Yeah. So Chang'e 5 was a pretty rapid mission carried out last December. The spacecraft landed on the moon on the 1st of December, settled there for a few days, and then basically scooped up samples of the moon's surface and shot off the surface again, rendezvoused with its mothership. This was fantastic stuff. That then flew back to the Earth and dropped a re-entry capsule, which landed on the 16th of December, which is not only Beethoven's birthday, but it was my late father's as well. While we're talking about birthdays, there you go. 16th of December last year. So that's when the samples landed. And since then, of course, they've been analysed to bits and analysed to death. I think there were about 2 kilograms. I think it was a significant...
Gee, that's a big chunk.
Amount. I should check that figure, but my recollection is that it was a decent-sized sample. See if I can verify that. No, I can't easily, but we'll find out later on probably. Anyway,
I'll try and find it for you.
Yeah, it's enough that that all the kind of all the armory of the Earth's laboratories have been able to be essentially directed to it. So it's had a really good, thorough going over. And what has happened is quite surprising, because the outcome is that these rocks are significantly younger, or the soil samples are significantly younger than what we saw coming back from the Apollo missions and the Soviet Union returned samples back in the 60s.
Oh, so when you told me we were doing this story, I thought you were going to say the opposite. So that's interesting. 1,731 grams.
There you go, nearly 2 kilograms. Yeah,
nearly 2 kgs.
Yeah.
Sorry to confuse all our American listeners with that metric.
What is it? 4 pounds?
61.1 ounces.
Yeah. Oh, that can't be right.
No, it doesn't sound right to me.
No, it's right. Yes, it's nearly 4 pounds. Yep. So okay. So it's a good solid chunk actually. These rocks are younger. So the critical thing here, Andrew, is where they came from, because the samples, the basaltic samples that came from the Oceanus Procellarum on the Moon, the ocean of storms, and Oceanus Procellarum is the only ocean on the Moon. And remember, the oceans are actually basalt plains, or the seas, are basalt plains. Most of them are seas, like the Sea of Tranquility, the Sea of Crises, all of those. But there's one ocean, which is the Ocean of Storms. And it's big. That's why it's called an ocean. It covers, from our perspective, in the Southern Hemisphere, it covers most of the right-hand half of the Moon. It's the other way around in the Northern Hemisphere.
Yes, it is.
And it's a very large area. And the other basalt plains, like the Sea of Crises, the Sea of Tranquility, the Sea of Rains, all of these, when you look at them on a map of the Moon, they're more or less circular. And they are impact basins. What happened was, in the Moon's early history, something big clouted it, an asteroid, made a gigantic crater, which is big enough to be called an impact basin, which then filled with basalt due to tectonic activity, probably following the impact. But Oceanus Procellarum's different, because even though it's still thought to be at least partly a large impact basin, I think it was the Grail satellites. There were 2 Grail spacecraft called Ebb and Flow, and Grail was, I think, Gravity Recovery and Interior Laboratory. That's what the acronym was. It's a NASA pair of spacecraft that sampled the gravity of the Moon and looked in particular for concentrations of mass beneath the surface, what are called mascons. They were called that back in the 1960s. And they found that Oceanus Procellarum was actually almost a rectangular basin with huge rift valleys delineating its 4 sides. It's a bit more untidy than that. But that led to the suggestion that its origin was actually volcanic, rather than being created by an impact. And so that's that's the thing that differentiates the Ocean of Storms from the other seas on the Moon. And so maybe it's not so much of a surprise that whereas the rock samples that have brought back from the Moon with the Apollo and lunar programs, that most of them were formed between 3.8 and 3 billion years ago. But the new ones, the new samples, are kind of half that age. I think 2 billion years is the typical answer. I'm just looking to see if I can find a more precise number, but I think there's a variation in years.
So that would mean this is fresh rock that's been volcanically layered
That's
on
right.
that.
Yes.
Yeah.
Yeah. And it is. It's younger than 2 billion years old. That's the bottom line with this story.
And they didn't just scratch this off the surface, did they? They did a bit of digging. I believe they did a 1 meter core sample.
Yeah, it was. Yes, that's right. It's not just surface soil. And yeah, the answer is the typical age is 1.97 billion years. So, definitely younger. So the interesting thing now is to work out how that could have happened, because the moon is relatively cold in its interior, and volcanism is something that we think has now essentially died away. So something happened that basically created volcanic activity at that relatively late time in the moon's history. So,
do we know what the moon would have been like environmentally 2 billion years ago?
Not much different from what it is now, in fact.
So that does make it a rather interesting mystery.
Yeah, that's right. So there's a local aspect to this story as well, because people at the University of Queensland are working with the Chinese scientists who've been doing this. There are also members from the US, the UK, and Sweden. And apparently the lab in which these analyses were done is among the best in the world. One of the scientists from University of Queensland says they did a phenomenal job in characterizing and analyzing the volcanic rocks samples. So really interesting stuff. So the puzzle is why the moon sort of erupted into huge volcanic activity. I mean, this Oceanus Procellarum is about 2,500 kilometers across. It's not small. So I think that's I think it's a story still that's still being told.
So once again, a discovery creates so many more questions.
Yes.
How could this have happened?
Yeah.
And the analysis seems pretty clear that yes, what we have discovered is younger rock that was volcanically distributed. But how did that happen if there was no activity on the moon of that kind that we know of?
Yeah,
it does raise so many questions, doesn't it?
Yeah, that's right. One of the scientists involved says that by the time the moon had by 2 million years ago, the moon had begun to cool. The amount of magma being generated dropped off quickly, and one of the suggestions is that residual radioactivity in the moon's interior, with isotopes like uranium, thorium, potassium, basically produce the heat necessary for this late volcanism to occur. But then there's another puzzle, because the Chang'e 5 samples don't show those radioactive elements in the material that they've sampled. It is a puzzle. There's another suggestion that's been made too, Andrew. I'm just throwing them into the mix here.
Sure.
And that is, we know that 2 billion years ago, the moon was significantly nearer to the Earth than it is now, because it's got this constant drift at the moment. It's 2.36, I think, centimeters per year, drifting away from the moon. Actually, no, it's about 3.6, if I remember rightly. I should get my numbers right. 3.6 centimeters per annum drifting away from the Earth, the moon drifting away from the Earth. So 2 billion years ago, it was much nearer. And that means that the tidal effects of the Earth on the moon would be, squeezing and squashing the moon much more than it is now.
So like a gas giant effect.
The effect of Jupiter on Io, exactly,
yeah.
That we've got this volcanically active body orbiting Jupiter. We may well have had a similar phenomenon on the moon. So there might have been volcanism on the moon later than people thought.
Toothpaste tube theory.
That's it. That's the one.
Yeah,
yes.
Just squeeze a little lava out, put a little love in your heart, that kind of thing. Yeah. Okay. Well, yeah, that may well be the piece of the puzzle that's missing, but I suppose I'll have to do a lot more work to confirm that. But it's got to be something simple. It's always got to be something simple.
Well, we hope so we could talk about it.
Yeah, indeed. While we're still on the moon, I just picked up on a story today that when NASA goes back to the moon in the not-too-distant future, they'll be driving around a rover, an Australian-made rover, which I think is very exciting.
Yeah, it's a robotic one, and it will likely precede the human landings. We don't know that for certain yet, but I think 2025 is when this Australian-made rover might well be deployed, and that's now, I think, the date that people reckon that astronauts will return to the moon. So
I've already seen some of the schematics, and it's shaped like a Holden Ute. It's going to be a ripper.
Yeah. It'd have to be, really, wouldn't it? Yeah.
I reckon.
With the word
so.
Bonzo written on the side or something like that.
Yeah, the People's Rover, it's going to be called. The People's Rover. All right. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a short break so I can tell you about our sponsor, NordVPN. Now, a virtual private network is something that I think a lot of people need these days. There are so many scams and so many hackers and so many criminals out there trying to get your data, and they do it in unsavoury ways, and they do it very cleverly. As time has gone on, hackers and scammers have been able to come up with more and more clever ways to get into your system. And a VPN service will certainly protect you from those kinds of people. I also recommend you don't click on links for emails that you are uncertain about, because that's another way they get to you. But NordVPN is the best in the business. It's the fastest. It's the most reliable. It is available on up to 6 devices on all major platforms, from Windows to iOS to your smart TV. Just about anything that you use that connects to the internet, you can protect through NordVPN. Now, one of the things I've told you about in terms of NordVPN in recent times is how fast it is. I've just connected my NordVPN and I've done a speed test. Now, I'm on a 50/20 plan, so 50 megabits per second download, 20 megabits per second upload. Now, those are numbers that you rarely achieve, given the wide use of the internet and the number of people that are logged on at any given time. I've just logged on to NordVPN through a Sydney server, and I've done a speed test. My download speed came in at 45.25 megabits per second, which is pretty damn quick, and my upload speed was 17.6. So that's with the VPN activated, which is pretty much the same and sometimes better than I get when I'm not connected to my VPN. So it's certainly a very reliable system. I have no complaints about it, and I certainly recommend it to you. We have a special URL so that you can get a special deal for NordVPN as a Space Nuts listener, and that is nordvpn.com/spacenuts. And as a part of that deal, you'll get 2 years plus 4 months, 2 years plus 4 months. And I think it adds up to about a 70% discount overall, just because you're a space nut. That's nordvpn.com/spacenuts. Check it out today and get yourself hooked up with NordVPN. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
And thanks for listening. Don't forget, you can become a patron of Space Nuts by jumping on our website and clicking on the supporter button, or you can just go to the URL patreon.com/spacenuts, and there, if you so desire, and it's not mandatory, you can sign up as a patron and chuck a couple of bucks in our bucket every month. And it just helps to keep this Space Nuts dream alive. So look it up, patreon.com/spacenuts, or if you're not a Patreon fan, you can do it via Supercast. There are all sorts of options, but best way to find out what we do and how we do it, and what we do with the money, which goes into the Fred Watson Pension Fund, is to go to our website and check it all out. Now, Fred, let's move on to the next story, and this one is another University of Queensland yarn, I think.
Yeah, and that,
in part.
I apologise because I attributed some of the Chang'e 5 story to the University of Queensland, which is incorrect. But there is an Australian component. So I do beg the pardon of various Australian universities. Don't want anything more to do with me. But the University of Queensland certainly played a part in this story that we are about to do now.
Which is about radio signals discovered from distant stars. Now, I think I heard something again in the news only today about these about radio signals being detected, and they haven't been able to exactly pinpoint where they're from, but they've picked up quite a few. I'm wondering if this is the same story, or if this is a different. It is, okay.
Yeah, it's the same story.
Yeah, we've got more wow signals by the sound of it. Well, maybe not wow, but wow, interesting.
What's a slightly less active version of wow?
Gosh,
that's it.
Signals.
Yes, they're gosh signals. Yeah, exactly. Good. Well, I'm glad we sorted that out.
Golly gosh and gee whiz signals.
So it's a story that originates actually in a radio telescope array in the Netherlands. So the Dutch National Radio Observatory, which is called Astron, has what is still probably it may be the most powerful low-frequency array on the planet, although the Murchison Wide Field Array here in Australia, which is also low frequency, must be close behind. But that low frequency array has an acronym that is LOFAR, the low frequency array. That's a really good one. In fact, it's not just in the Netherlands. I've visited some of the LOFAR sites, one in France, I remember, a few years ago. So it's an array of basically dipole antennas. They're not dishes. They're things fairly close to the ground, but the radio signals that they process are, as the name suggests, low frequency, and you don't need a big dish for that. You do it with dipoles. And in fact, the clever bit is you steer these things around electronically. You can point it in different directions. In fact, you can point it in different directions simultaneously. You do it all in the electronics. Very similar technology to what the square kilometre array itself will use. Anyway. Clever. So this is a study of radio signals from stars. Now, stars are not great at emitting radio signals because they, most of their energy is delivered in the visible light spectrum. However, these stars have been found to have radio emission, and they are a particular type of star. They're red dwarf stars. And they're relatively distant as well. They've looked at a selection of 19 distant red dwarf stars. Why do you get radio emission from red dwarfs? Because they're very active. They've got star spots. And they are regions on a star's surface, because they're highly magnetized, they emit radiation fairly copiously. And that's one reason why the sun is actually the brightest object in our radio skies, because we're relatively close to it. But there's all this activity, magnetic activity, going on the sun's surface, and it all emits radio waves. So that's all well and good. They've looked in detail at the way these radio signals from the red dwarf stars operate, but 4 of them are different, and they've got a different characteristic to them, and what that says is that something else other than the sunspots or the star spots on these red dwarfs is probably causing it. And the best fits to the data in terms of modeling is that these stars have planets which are experiencing auroral activity because the star itself is active. It's got star spots on it. That means that there's powerful solar winds, or star winds, if we can call them that, stellar winds, which would be interacting with planets in the vicinity. And if those planets have magnetic fields, then you're going to get aurorae. You probably get them whether they've got magnetic fields or not, but they'll be certainly more intense with magnetic fields on the planets, and that causes radio signals, and that is what they think they've detected.
Okay. So when we have aurorae on Earth, we are transmitting to the greater universe as a consequence. In fact, this week there was a large coronal mass ejection that's hit Earth, and they were worried it would cause electronic problems or interference. I haven't heard of anything, but apparently yesterday, in real terms, our time, there were some really good aurorae visible on the planet. So it was a big one apparently.
Yeah. Yes. There was lots of aurora pictures on Twitter this morning, I noticed, and I had a look at the sun either yesterday or the day before. I've got binoculars with solar filters on them, Andrew, so I can have a quick look at the sun from time to time to see what it's looking like. And there's a spot right in the middle of the disk, and that's the kind of thing that you might expect activity to generate something coming in our direction. So it all makes sense. Yeah. There's a bit more to this Astron story, because they're suggesting that that there is maybe material that's coming from these planets that's interacting with the magnetic fields of the planet and the subatomic particles coming from the from the stars themselves. And what they're doing is they're drawing a parallel with, once again, Io, Jupiter's moon Io, which is highly volcanic, and so it's actually churning material out into space, and that's what really amplifies the aurorae. If you've got dust coming from volcanic eruptions finding its way into space, that actually essentially it basically creates an environment that is more conducive to bright aurorae or to intense aurorae. Now, the thing about these distant planets is, of course, we can't see the planets at all. There's at the moment, I don't think, any evidence other than this that these stars have planets, but it's certainly work that will be followed up. One of the researchers, Benjamin Pope, who's at University of Queensland, comments. Actually, there's quite a few comments. I might. What his comments? There's a few comments from different members of the team. Benjamin Pope says, we can't be 100% sure that the 4 stars we think have planets are indeed planet hosts, but we can say that a planet-star interaction is the best explanation for what we're seeing. Follow-up observations have ruled out planets more massive than the Earth, but there's nothing to say that a smaller planet wouldn't do this. So, yeah. And what they've obviously done is looked for wobbles in the star's spectrum that indicate that a planet is orbiting these stars.
Are these 19 red dwarf stars in the same vicinity, or are they spread out all over the place?
I don't think so. I don't have details of how they're distributed, but I think they're all within a few thousand light years. But I think they're in different parts of the sky.
Okay. Yeah, it would probably be weird if they were all together.
That'd be even weirder. That's right. Yes.
Yeah. Okay. Well, there might be. Well, it sounds like there is more to learn from this, and they'll keep analysing the data, and hopefully they will soon be able to confirm or deny the presence of planets orbiting those respective stars.
Yeah, and just making the point that I made at the beginning of this story, with the square kilometre array, which will hopefully switch on in around 2029. This will amplify not only the stars that have already been observed, it will give us much more information in much greater detail, but also will let us see out to much greater distances.
Awesome. Okay.
So, yeah.
We continue to watch with interest.
That's right. I think these are relatively local. I did say 1,000 light years or so, but it's actually, I think, more like a couple of hundred light years, the maximum distance of the ones that have been observed. Whereas thousands of light years will be possible with the square kilometre array.
Yeah. How? Just a question popped into my head. How common are red dwarf stars?
They're the most common stars by a long way in our bit of the galaxy.
There you go.
So I think it's something like 70% of all stars in our neck of the woods, and actually probably throughout the galaxy because we're a relatively normal sample. But yeah, something like 70% are red dwarfs.
Would they be livable? Orbiting?
That question's been asked a lot, particularly in regard to Proxima Centauri, which is a red dwarf and the nearest of all stars to our solar system. And the thing that makes them probably not the ideal places to find life is exactly what we've been talking about, the fact that these stars are very active magnetically. So you're constantly blasting, super fast clouds of magnetized particles into the vicinity around them. They suffer from solar flares and all the kinds of things that would be damaging to evolving life.
So you'd need SPF 50 million plus or something.
Yeah, probably. I don't even know that only stops the electromagnetic radiation. It's the other stuff that's the dangerous stuff. The protons and electrons riddling your body. High energy.
Okay. So, important safety tip: do not live on a planet orbiting a red dwarf.
That's it. Yes, that's a good safety tip.
Yes, indeed. This is Space Nuts with Andrew Dunkley and Fred Watson.
Space Nuts.
Now, if you are someone who enjoys social media, let me tell you about our Facebook page. Now, there are two Facebook pages, just in case you're confused. There's the Space Nuts Facebook page, which is the official Space Nuts Facebook page, where we upload stories fairly regularly for you to read and learn, and obviously we upload our podcast links there as well. But you can also join the Space Nuts podcast group on Facebook, which is a user-generated page. The listeners created it, and that's where you can get together and have a chinwag and ask each other questions and come up with theories that people can throw their ideas at. It's a fun group and very much worthwhile getting involved with. So join them both, facebook.com/spacenuts and the Facebook page dedicated to Space Nuts listeners, which is the Space Nuts podcast group on Facebook. I've got a headache now. Let us, Fred, move on to some audience questions. We've got a few to deal with today. The first one comes from Dr. Robert Scott.
Hello, Fred and Andrew. Dr. Robert Scott here from the Sunshine Coast. And I have a couple of questions for you. So firstly, what is the temperature of a black hole? If they absorb all matter, light and energy in the space-time around them, surely they should have enormous amounts of energy, boiling like a million stars, but I suspect they may be very close to absolute zero as the extremes of physics are reached closer to a black hole. I'm guessing this also affects the behaviour of atoms, which determine temperature. Second question, what is space-time made of? It has ripples in it, theorised by Einstein and demonstrated in 2015 by LIGO. So surely it has other properties. Mass bends it. We know it's fairly rigid. It's smooth. What else do we know about the properties of space-time? And thirdly, could Professor Fred please explain to me the missing matter in the universe problem? Couldn't we just have an enormous error which is proportional to the magnitude of our universe, which we also don't understand? Or could the properties that I alluded to in my second question about space-time and what it's made of, could this account for the missing matter problem? Thanks very much, guys. Thanks for a fantastic podcast. Keep up the good work. Talk soon.
Okay. Thank you, Robert. Lovely to hear from you. A triple bunger. I thought he only had two questions. He must have snuck that one in while I wasn't looking, that last one. Yeah. The temperature of a black hole.
Yeah, well, he's right. It's very close to absolute zero on the inside. And in fact, you can work it out. And it varies with the mass of the black hole in a very subtle way. The more massive the black hole, the colder its temperature is. Exactly as Robert says, it's because you're looking at extremes of physics that this is the case. Immediately outside the black hole, the temperature is hundreds of millions of degrees, because that's where the matter is swirling into the black hole and jostling together, and friction raises the temperature, and that's why we can see black holes, because of the energetic emission coming from their accretion disk, the disk of swirling material around it. Yeah. But the black hole itself is very cold, and I'm just kind of having a look to see what's available on this. There is a calculator. You can, if you Google or whatever search engine you like to use, put in black hole temperature calculator, it will take you to this calculator, which is very simple. You put in the mass of the black hole, and it tells you what the temperature is. And I can tell you that for the sun, the temperature is for a 1 solar mass black hole. Let me say that, because this is not the sun itself. It's a black hole of the mass with the mass of our sun. It's 0.0000006172 degrees Kelvin. So it's well under a millionth of a degree there. It's it's about a tenth of a millionth of a degree.
Okay. So, within the black hole, it's almost absolute zero, but outside, it's a boiling froth of hell.
Yeah.
Okay. All right. The second part of his question was, what is space-time made of?
And
Plasticine.
Dark
matter.
What Robert has done there is said kind of what we know about space-time, and that's more or less what we know. There's probably one other thing I would add to it, in that you can get these virtual particle pairs being created within space-time. Something funny happens, but it's an entity that, in a sense, it's a mathematical entity, Andrew. But it clearly has reality, because we do observe distorted space-time in many different ways, either by gravitational waves or by gravitational lenses, which are extraordinary phenomena in deep space. And in some ways, we've gone back to an old idea which was demolished in the late 19th century, which was the idea of the ether. And the ether was supposed to be the medium that transmitted light waves, and that was demonstrated not to exist, because if that was the case, the speed of light would vary. It would depend on where, what your speed is, what the speed of light would look like. And so as soon as you say the speed of light is always, in a vacuum, is always the same, then you've got rid of the ether. But you still haven't got rid of the idea of some fabric of space. That's in many ways the best way to describe it. And it's a woolly term. I might have a bit of a look in the physics papers to see if I can get a better answer than that. But it is really very, very hard to wrap your head around that it's nothing, but it's not nothing, because it can bend.
Yeah, well, I suppose you say the same thing about dark matter and dark energy. It's something, but we don't know.
Yes,
we don't know what.
Yeah.
And the third part of his question was the missing matter question, which I guess is somewhat related.
Yes, that's right. So I'm assuming by this that Robert means the missing baryonic matter. That's normal matter as distinct from dark matter. Dark matter is something that has a gravitational influence but doesn't interact with normal matter in any other way. So we can't detect it directly or measure it, at least under normal circumstances. It's possible that very rarely dark matter might interact with normal matter, and that's why people are building laboratories like the one underground at Stowell in Victoria here in Australia. However, the dark matter is something that, whilst we don't know what it is, there's a really good, I suppose, a good chance that it will turn out to be a species of subatomic particle that we haven't yet identified. And there are various candidates in various theoretical models that people have. And I think that's reasonably well accounted for. However, and I think this is coming to the nub of the question, when you look at baryonic matter, normal matter, there is still a fraction of that hasn't been detected. Now, how do we know that? And the answer is that when you look at the universe on very large scales, like the whole of the visible universe, we do things like mapping out the matter of the universe by doing galaxy redshift surveys, some work that I was involved with a few years ago. That lets you take stock of the energy and matter content of the universe, because you can look at the way these galaxies are distributed in space, and that actually you can convert to a numerical estimate of what the mass distribution is. And it's not just mass, it's matter and energy. So the energy we know is dominated by dark energy. So something like 70% of the mass of the mass energy budget of the universe is dark energy. Around 25% is dark matter, and about 5% is baryonic matter. That's the stuff that is normal matter. But we don't see that 5%. We only see about half of it. And probably the best explanation for what that missing matter is has come from work done on fast radio bursts, which has shown that there is a plasma that permeates the whole of space, electrons and probably protons as well, which has probably enough mass to account for the missing matter. That's a long answer to a short question, but it's just to make sure that I understand the particular brand of missing matter that Robert's asking about.
It could also be missing biros and pens.
There's that too, yes. And, well, when you get to a certain age, it's missing pairs of spectacles.
I've reached that age.
Yeah, so have I.
All right. Robert, thanks for your question. Hope all is well on the Sunshine Coast. To our final question today, this comes from a place we affectionately call the Gong, otherwise known as Wollongong, south of Sydney. This is from Martin.
Hi, guys. It's Martin from Wollongong here again. I have a question about Jupiter and I guess other gas giants as well. In the last 4.5 billion years or so, there must have been billions and billions of tons of rocky asteroids that must have hit Jupiter. If that is the case, why is it still a gas giant and not a rocky planet with a huge atmosphere? Or does it actually have a rocky core? If it doesn't have a rocky core, what happens to all the rocky stuff that hits it? Why doesn't it travel down Jupiter's gravity well to the center of the planet? Or does it just get smashed up and get blown around in the winds as dust? I guess taking it to the next level, what would happen if an Earth-sized rocky asteroid or two with an Earth-like composition crashed into Jupiter? Would that be enough to change Jupiter into a rocky planet, albeit with a huge atmosphere? Be interested to hear your answers on that one, guys. Thank you.
Thanks, Martin. We were only talking about the red spot on Jupiter last week and how it's the same size as Earth. So I would venture to say an Earth-sized asteroid probably wouldn't, Jupiter would go, ho, ho, ho. That's all.
Okay. There's a multitude of things to talk about there. Let's talk about the impact of asteroids today. The entire asteroid belt, Andrew, has a mass of 4% of our moon. The entire asteroid belt. weighs 4% of the
Wow.
Earth's moon. So you're talking about, just the last vestiges of debris of the protoplanetary disk, the disk that was around the sun in the early solar system that formed the planets. So Jupiter, things do hit Jupiter. They basically just vaporize in the upper atmosphere. There was one only a couple of weeks ago, I think.
That's true, yeah.
An impact event on Jupiter, which was recorded by amateur astronomers. Great stuff that they can do this.
Yeah.
I watched the videos of it, and it just vaporizes because it's hitting at high speed, very like the things that hit the upper atmosphere of the Earth. And, there's no possibility of a planet-sized object hitting Jupiter and the way the solar system is at the moment, because it's utterly stable in terms of planetary orbits. However, it wasn't always like that. And in the early solar system, it was the interaction of asteroids together to form planetesimals and then protoplanets that gradually built up the planets. And the planets were formed by collisions by asteroids. Now, in the case of Jupiter, Jupiter is above the frost line, or beyond the frost line, which means that some of the volatile materials that were in the dust and gas cloud that formed the solar system, they freeze out. And so as planets are being built in the solar system, when you think of it, the ones beyond, the frost line is actually between the orbits of Mars and Jupiter. So beyond the frost line, you're going to get not just rocks coming together to form planets, but also ices as well. And that is thought to be why the gas giants grew to be giants, because their cores could accrete not just rocks, but icy material as well. In fact, ices probably help the dust grains stick together when you're forming planets. So out there in the cold reaches, you're going to form much bigger planetary cores, and it's because those planetary cores are big, and we don't know whether they're rocky or not. Some people think it's metallic hydrogen that's at the core of the gas giants. Whatever it is, it was big enough for these planets then to collect an envelope of gas around them as well. It's because they are so massive that they've been able to collect an envelope of gas, and that's why they look like the way they do today. So this process did take place very early in the solar system, but it's you're now dealing with really giant planets, much bigger than the 4 rocky planets, and that is they're very stable because they're so big, they're so massive. It's unlikely that anything's ever going to hit them that's big enough to disturb that.
It sounds like it would take a staggering amount of material.
Yeah,
and
exactly.
It doesn't sound like there's that much material out there anymore.
No. I should say, though, that it's probably the mass of Jupiter, because it did get so massive very quickly in the early solar system. And the main asteroid belt, the remnants of the protoplanetary disk, that would have been much more massive in the early solar system. But it's probable that some of it's been accreted by Jupiter to make it so big, but a lot of it will have been just gravitationally slingshotted out into space by the influence of Jupiter. So it's probably, the solar system's left behind a trail of debris as it's wandered its way around the centre of our galaxy.
Okay. Thank you, Martin. Lovely to hear from you, and hello to Wollongong. I know we've got a fair few people that listen to us down there. That brings us to the end. Fred, by the way, if anybody would like to send us questions or just comments, you can do that via our website, spacenutspodcast.com, and just click on the AMA tab up top, where you can send us an email or send us a voice message or voice question, or you can go to the right-hand side of our homepage and it says, send us your voice message. You can do it that way as well. So if you do have any questions for us for future episodes, we'd love to hear from you. We do get a lot of the same kinds of questions over and over, which is good. It means everybody's sort of on the same wavelength. But when we answer one, we answer all. So sometimes your question might not see the light of day, but that's because we already answered it, or we just say, "Oh, we don't like him." We won't answer that one.
Or
Not true. Not true. Even though Fred told me to say it. Not true.
no, it's not true.
All right. Yeah, we'd love to hear from you. So wherever you are, send us your name and your location and your question via our website, spacenutspodcast.com or spacenuts.io if you prefer. That's it, Fred. Thank you for your time again today. It's been a lot of fun and good to catch up.
Indeed, and we'll speak again soon, Andrew. Nice to talk.
We will. Yeah. We will indeed. Professor Fred Watson, astronomer at large, part of the team here at Space Nuts, and thanks as always to Hugh back in the office, straightening out all the paper clips as he just loves to do because he's so busy. And from me, Andrew Dunkley, thanks for your company, and we look forward to having you join us again on the very next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.